Good. Well, thank you very much, Helen, for the kind introduction and for the invitation to be part of this special Geo Summit this year. It's unfortunate we're not together in Switzerland, but maybe next year, hopefully. So as Ellen said, I'm Jean Hutchinson, and I'm very pleased today to present to you a talk entitled Combining Remote Sensing Data and Simulation to Improve Rockfall Event Forecasting. First, I'd like to acknowledge the team of people who have worked with me over the years on these topics. They include quite a number of graduate students and postdoctoral fellows, many of whom are in industry now, continuing to work on these types of topics and addressing issues of geohazards in many locations around the world. In particular, this talk focuses on issues related to rockfalls and debris flows, and also to the development of simulation using game engines. And so on this slide, you can see the color coding of the various participants in the research projects, depending on their most specific focus. So the problem we're dealing with is that rock slope failure events are complex, often have multi-stages, and warning signs are often not detected in advance, especially in more remote locations. And so the video we're about to see was recorded on tracks where they observed the failure, stopped all traffic, and then they watched the event unfold. So when you watch the video, you'll see that there is rock already on the track. You can see a subsequent failure that they've captured that is also over the track. And then you can see some small events starting from the top right of this image. And then eventually another failure continues to occur. So you see that happening just now. You see an additional failure. And I think what's illustrative about this video is the fact that there are a number of events that you record, but also the fragmentation. So when we simulate rockfalls, as you'll see later, very often we're simulating a single rockfall event or maybe a couple of rockfall events. And you saw in that video that the rocks tend to fragment substantially. And so that's something we're trying to address in terms of the simulations that we do. The research I'm talking about in this presentation was all developed under the Canadian Railway Ground Hazard Research Program. And this is really focused on geohazard exposure on the railway tracks. As you can see on this slide, there are over 40,000 kilometers of railway track in Canada. And you can see around the outside of the slide a variety of pictures of locations where track has been built. The problems here are multiple, but they include the fact that many of these tracks were built over 100 years ago with non-current geotechnical techniques. They go through diverse physiographic regions with substantial depths of freezing and thawing over our winters, variable soil and rock conditions, and also very active geomorphic processes and climate extremes. Because the railway tracks were often progressed along riverbanks and in valleys, they're exposed to all the hazards that are produced from those kinds of environments. The team within the Railway Ground Hazard Research Program are shown on this slide. They include people from both the main railway companies in Canada, CN and CP. The other university involved is the University of Alberta. And then we also have the Geological Survey of Canada and Transport Canada involved in the project as well. So it's a really unique project from the perspective that we have both the main railway companies, the Geological Survey, and the regulator of railway safety in Canada. We're very fortunate to have had 3 phases up till now, over 15 years of research together, and we're just embarking in the 4th phase from 2020 to 2025. So it's a long-standing research program addressing the problems we saw on the previous slide. Our focus has been on the hazards that you see on this slide. So we're working on landslides on the left side, large retrogressive failures in the prairie provinces. We're dealing with larger rock slide and smaller rockfall events. We're dealing with hydraulic erosion, and then we're dealing also with snow avalanches and debris flows. So all of these hazards individually or even multiply in some locations can result in unsafe track at the allowable train speed. And again, if you think about the fact we have 40,000 kilometers of track, that's a lot of exposure. In the areas that I've focused on specifically recently, the slope hazards can include the rock falls and rock slides. such as you see in the White Canyon on the left side, or it can deal with Quaternary glacial deposits such as you see on the bottom right side. Some of the impacts on infrastructure can be seen in these slides. On the left side, a small debris flow from within the White Canyon onto the tracks. You can see an excavator clearing that away, and then traffic is resumed once the track is deemed to be safe. And very often these occur during large rainfall events, as we're all aware, and they happen often as well at night, as you see on the bottom left side. And then rock slides and rock falls on the right side of this image can impact the infrastructure, and certainly if they're a larger event, impede the traffic through the area. What you see on the top right are the systems that are used along much of the track called slide detector fences. So when the wires on that system are broken, it sends a signal which stops the rail traffic in that area. So the main objectives in terms of managing rock slope instability are shown on these next series of slides. And mostly what we're dealing with are large natural slopes. And in these circumstances, such as you see in this picture, it's very difficult to identify which features might generate falling rocks the next time. If you look at that slope with a practiced eye, it's very hard to understand where the next failure might occur from, because much of this slope has the potential for instability. How do we observe and measure the potential source zones and failure volumes? So here we see a slightly closer view of some of those rock slopes in Western Canada, and you can imagine that trying to assess that rock has a lot of challenges. The key element that we'd really like to move towards is forecasting potential failure. So how can we assess the rock slopes so that potential failure in the future is anticipated, warning is given, and protection is made? So the picture you see on the right side is of a site that's been monitored by the railway geotechnical engineers for many years. It looks very unstable, but to date has not failed. And so how do we forecast when that might fall? Then once we've identified the potential source zones, what's the risk to infrastructure? So in this picture, you see again the slide detector fences between the slope and the railway tracks to provide warning should a failure occur. But the key thing here is, how do we protect that track? What will the run-out distance of any failures be? What kind of energy and bounce height? The kinds of things that anybody working, say, with the GeoBrugg systems would be used to thinking about. And finally, how do we anticipate the types of events that we might have, and how do we design effective mitigation for those events? So in this, you see some draped mesh trying to maintain the rock falls in the ditch area. And we also see other methods that are being used here to protect the tracks. Again, on the top right, the slide detector fences and ditches wherever it's possible to build them. But you can see that in many of these locations, the amount of space between the tracks and the river and between the tracks and the upslope is very limited. So the ability to build ditches is fairly constrained. We have rock sheds of many generations on these tracks, as you see on the top left. Occasionally tunnels, although not anything at all like the kinds of tunneling we see in Europe. We have many fewer tunnels here in Canada. And then on the bottom right, we see a barricade wall with, again, a high energy fence on top of it. So this is another method of protecting the track from rock falls. Given what you've seen, these slopes are hundreds of meters high, often in very constrained locations. These tracks are very busy, so access to the tracks is very limited. Otherwise, it affects the capacity of those tracks to carry goods and passengers. And so we're working with complex, largely inaccessible slopes where the consequence of failure is high. And so how do we start to address this issue? In the next section, you'll see a video taken from a small UAV over the track that you see in this photograph. And you'll see the rock shed that's at the bottom of this picture, and you'll see the river in what I'm about to show you in the following video. So in this video, we're flying above the tracks, we're flying above the rock shed and above the Thompson River. We can see large spires of rock protruding out of the slope, which are diabase dikes. We can see channels of debris that move down the slope across rock sheds. We're just seeing that now. Again, we can see 3 different generations of rock sheds in this section of video, And again, you can really see how tightly constrained the topography is here in terms of the position of the slope, the position of the track, and then the river right beside it. So there's very limited space to do much about these issues. The other unique thing in Canada is that we have two sets of main railways that went across the country, and we have CN usually on one side of the river and CP usually on the other side of the river. So the ability to move tracks is fairly limited as well. So now I'll move on to the way that we collect data from a remote sensing perspective. We've been doing this work for several years, and you can see on this slide the different ways that we collect the information, whether it's from a terrestrial or an aerial perspective. And we use LiDAR, photography, and INSAR for these types of approaches. So two major classes of data products are generated from our work. The first are products that give you a visual record of the surface condition. So in the picture on the left, you see David, one of my PhD students, working with equipment, and the equipment closest to him is a camera on a tripod using a gigapan head. And then later I'll talk to you about the LiDAR system, which you see on the right side of this picture. But for now, what the gigapan system does is gives a series of hundreds of photographs perfectly overlapping so that you can generate a high quality panoramic image. There's no geometric information in these, it's just purely a photographic record. But you'll see in the next slide the way that that helps us interpret what's happening on slopes. So here's a picture of one of the Quaternary deposit slopes that we've talked about a little bit previously. This is a location where there are river deposits that are standing in high cliffs, and we see events that occur falling from these slopes down towards the track. And what I'll ask you to do is look sort of middle of the picture. There's a relatively large rock that you can see middle of the picture, and I'll just show you a series of screen grabs from the gigapan image, simulating what you can do with this data. So as this runs forward, you can see us zooming in on a large rock in the slope. And what you can see in the closest picture is layers of silt and sand, cobbles, gravel boulders, and you can see, in fact, the individual layers within the silt bands as well. And so this is the quality of image you can gain from these gigapan systems. So the final image in this sequence permits you to look at the overview of the gigapan and then the close-up view. So that's the kind of photographic information we gather. Next, I'll talk about the other class of data that we generate, which is a detailed record of the geometry of the surface. Many of you may be aware about the work with LiDAR that many groups are doing around the world. In this case, data is produced from a pulse of light that is sent out and reflected and recorded by the system. And that pulse permits you to understand the detailed geometry of the slope because it gives you a detailed distance record to each point on the slope. So each point in the point cloud that results from this has unique XY coordinates and represents in detail the geometry of the slope. The picture that's now showing on the right side of the slide is a picture of the point cloud. So this doesn't have any photographic information. This is purely the XYZ geometry information of the slope. So now I'm playing a video fly through of one of the point clouds. You can see again the rock sheds that are present in this area. You can see the debris channels. You can see the diabase dikes again protruding from the slope. And you can see that in this instance, you can get a lot of detailed information about the geometry. You can also see locations which are shaded because you can't see them from the terrestrial vantage point. And so those are zones where you don't have any information and they're occluded from view. The next slide is photographs taken from a helicopter. So in this case, we're developing a model from photographs to again permit us to view this in 3D. So we've used the PhotoScan software, which uses structure from motion techniques to combine the photos, and we can create a 3D photogrammetric model from that. So now I'll play this video, which is a 3D model built from 92 photos taken from the helicopter. In this case, you have both geometric information and photographic information, so it really lets you start to understand the geology and geometry of the slope. Again, some locations which are occluded, but this is a really good model for working with this kind of data set. So this provides a nice combination of both the geometric and the photographic information. So now when we look at these sets of information, if we start to collect this data on different times at the site, we can now start to do detection of change between the detailed geometric models that we've built. And this permits us to start to look for locations on the slope where material is lost and gained. And so the sequential data sets, depending on how far apart they are, can give us information about, say, daily or weekly or monthly change on the slope. Over the last 15 years, my research group and some others have been working on the models and the way we can interpret them to get more and more detailed information. On this slide, you can see on the left side the simulation of a piece of rock that is detaching and rotating away from the slope with times 1, 2, and 3. And you can imagine that if you had the vantage point across the river valley that we have, you would see that section of the rock, which is highlighted in purple, is moving towards you. So in terms of the change detection, this would show you a gain on the slope because the material is moving towards you. It appears that the volume is increasing. Eventually, when the rock falls off, you now have a loss from the slope. And now you see the change detection indicates that a volume is completely moved from the slope. The image on the right side of this slide shows you the locations where we have gain and loss from these change detection approaches. So higher up on the slope, you see locations where there's gain occurring because rocks are falling from higher up and accumulating in the debris channels. And you can see down near the tracks quite a lot of loss. This is a period of time when they were doing maintenance work on the tracks, and so they removed material from on top of the rock sheds, and they also blasted some material from the rock slopes. So when I play the next animation, you'll see where the gain and loss has been occurring on the slope. So in this more close view, again, you see the loss of material as they clean off the rock sheds, some gain of material onto the flat-topped rock shed, loss of material from the rock spires where they've done some blasting work. So this permits us to track what's happening on the slope. And a key thing in our research is distinguishing between the sections of slope lower down, which have anthropogenic change, and the parts of the slope higher up, which are not affected by any human interaction. And so it permits us to actually look at slope management and natural slope processes. So now in the final slide on this section, I'll talk to you about combining the data sets. So on the right-hand picture, we see a comparison over 5 months of the Quaternary deposit where we see different loss and gain. And I'll just focus in on the part that's highlighted as a 5.8 cubic meter failure. And so if you look just at this change detection result, it would be hard to understand exactly what's happening. But with by combining the gigapan and the LiDAR information, we can zoom in to really understand what's happening. And so now on the bottom left, you see the zoom in on the gigapan, and you can see locations where there are larger boulders present in the deposit, and those have fallen out over time and created the loss of material that you see in the LiDAR imagery. So together, these two data sets permit us to really start to understand in a detailed sense what's happening on these slopes that are inaccessible for on-foot reconnaissance and work. The next component of what we can do is detecting major joint planes to do the type of geomechanics analysis that many of us do to think about instability of slopes on planar or wedge sliding or toppling. So this permits us to do the kind of mapping we would do on foot, but from remote images. We can also map the lithology on the site. Generally, it's really great if you can get some outcrop access to understand the rock mass close up, but then extracting that information and applying it to mapping the whole slope is easily done when you have the photogrammetric models, which give you, again, that combination of geometry and photography. So on this slide, you can see how we've applied what we learned at outcrop access along the railway track to mapping the whole slope and the lithology across the whole slope. The next slide shows us the distribution of rock falls over a 15-month period divided by volume. So in the upper one, you can see the thousands of rockfalls that have occurred that are smaller than 1 cubic meter on this site, the hundreds that have occurred in the 1 to 10 cubic meter size, and the less than 100 that have occurred in the greater than 10 cubic meter size. So we can start to think about the volume and the lithology of the source zone. And when we put this together in the work that Megan did, we can see the cumulative frequency magnitude type of diagram that many of us use for thinking about these types of hazards. In this case, what's really nice is we can divide it on the basis of the lithology, which then permits us to start being more focused about how we address the hazards induced by the different rock types across these sites. This then permits us to develop a rockfall database. And what you can see in this slide is the information that we record. And we have tens of thousands of events now in these rockfall databases from monitoring these slopes. We have information about the geometry of the slope before and after a failure, as you see in the upper pictures on this slide, and that was a 32 cubic meter failure. You can also see the same type of information for a much smaller failure, a 4 cubic meter failure. And if you imagine that most of our vantage points are hundreds of meters away, generally we would not get the information we do about these smaller events. They would happen, be captured in the ditch, and no one would really be aware that they'd happened. So what we can do in the database is think about the time to failure based on how often we scan the site, the XYZ location and volume. And then as the failures occur, we're also tracking what kind of structure was involved, what kind of failure mechanism was involved, and the shape of the rockfall. And we relate that to the lithology and the other information I've just spoken about. So this permits us with the remote sensing information to really build through a comprehensive rockfall database from natural slopes. The value of the database can be divided into whether you're looking at the information prior to failure or post-failure. So prior to failure, with the change detection work, we can see deformation and get some idea maybe of what the magnitude of the failure will be in the future to forecast that. And we can look at the rate and duration of the deformation before failure occurs. And at this stage, we can also anticipate what the failure mode might be based on what we can interpret of the sliding plane geometry. But prior to failure, that's hidden behind the rock that will eventually fall, and so this is really an educated guess. Post-failure, however, we can look at information about that backscarp, but also we can find some locations where we see the impact of falling blocks related to fragmentation and deposition at the toe of the slope. So the picture on the right shows a location where an 18 cubic meter failure occurred. You can see the impact positions down the slope as the rockfall fragments, and you can see the deposition of the material at the base of the slope. And we've also provided a cross section to show you the before and after geometry of that rockfall. One of the things in back analysis that we're starting to see very clearly is that for months, in this case a month and a half before this failure occurred, there was deformation that we could track. Now this is back analysis of a larger failure. We're hoping as time goes on to move towards forward analysis and to capturing these kinds of deformations early on so that we can start to forecast when they might occur. In this case, we can see that deformation started at least 200 days before this failure occurred, but we really picked up significant deformations about 50 to 60 days before the failure occurred. The other nice thing about having this data set is we can see how this rock topple, in this case, starts to move out from the slope. So we see accelerated deformations at the top of this block, numbered 1 and 2, and slower deformations at the bottom of this block, numbered 5 and 6. So we now start to be able to look at the magnitude and rate of change leading to failure, and eventually this should lead us to find the kinds of thresholds before failure occurs. When we take the information we're seeing, we can integrate the geology and the rock event characteristics into a better understanding of what's happening on the slopes. These pictures show you another event, a relatively small event, 1.4 cubic meters, which started up just to the right of the rock shed. You can see a mid-slope bench, which has been highlighted with the dashed line in the left-hand image. And you can see the talus pile at the base of the slope. And you can see a scale bar there of 7 meters to give you an idea that we're quite close to the slope in this case. The photographs permit us to look at the geological setting and the size of the blocks that have accumulated at the base of the slope. We can look at the before and after shape of the rockfall event in green and gray, and we can see structural mapping of the structures that are present on this slope. And when we put this together in the object you see on the right, we have the before and after shape of the rockfall. We have the presence of the structures that are present through the rockfall object. And this permits us to really think about how this rockfall might occur, what kind of impact it has, and start to build a simulation model that's based on detailed information. So this surface information lets us look at the source zone, the depletion zone, the shape of the object, the position where it impacts, and the fragmentation. In this simulation, we can see one of the game engines, physics engines that we're working with to simulate rockfalls. So we see that small event detaching from the slope, we see it fragmenting on the structures that we mapped, and we see a simulation of where the rockfall objects impacted and deposited. In this case, this result is the result of several simulations so that we can see the variability in potential behavior of these rocks as they move down the slope. Now we can move on to thinking about how we start to forecast and anticipate failures, now that we've built these systems for monitoring and we've built these systems for modeling. So now in this image, we see a location where an eventual failure occurs, and with the red arrows, we're highlighting some precursor, much smaller events that give us some idea that something might be happening on this slope. So in several circumstances in all the monitoring we've done, we found cases where small precursor events give an indication that something might be about to happen. That permits us to forecast that a rockfall might occur, permits us to give the railway engineers that information, and then they can think about the impact on the slope and mitigation that might be required. So here we see the events that have occurred around the boundary of this failure and the deposits of rock onto the talus slope prior to failure. Now we see on this left side of this picture the volume change associated with that failure. So we can see the loss up on the slope, we can see the impact positions on the slope showing as blue, and then we can see a mid-slope and talus cone location of deposits. So we see the red showing us where the material has deposited on the slope. And if we look at the gigapans again on the right side, we can see the before and after photographs of the rock slope before and after the failure occurred. And the nice thing about this is we can start to get a sense of the block sizes. So we can get a sense of what's deposited on the talus cone, how big are the blocks, which permits us to start calibrating our models in a much more effective way. So this rock slide was 158 cubic meters and 400 plus tons, but this occurred over an existing rock shed, so there was no impact on the track. So the physics engines that we're starting to use are a very valuable tool in geotechnical modeling. These have been developed for the gaming and movie industries, where, say, a flying bullet must be simulated in real time with real physics. And so the development that's occurred has been transformational, really, in terms of our ability to model. So what this lets us do in our world is simulate rock collisions and fragmentation in a very rapid, almost real-time sense. These engines also let us efficiently and realistically build worlds. So we can take our LiDAR data sets and build the type of modeling world that you see in this image. So when I run the video in a moment, what you'll see is the red block up on the slope that is taken from the previous slide's change detection. We've assigned a certain size of fragments based on mapping of the rock slope, and you can see as this proceeds how the rock fall occurs, how particles interact, and where they deposit on the slope. This was done about a year ago, and since that time, the ability to model fragments has increased dramatically due to some new changes in the game engine. So as time goes on, we can see increasing abilities to model these in more and more detail. So if I play the simulation, you'll see the rock fall starting to occur. You can see it disaggregating on the slope, blocks falling, impacting mid-slope, moving down and across the talus cone. And you can see the size of the particles, which are based on the photographic evidence we have of the eventual size of the fragments as this rockfall occurs. You can see in the final stages of the simulation that some of the blocks interact with one another, fall on each other, and induce additional delayed failures. It's realistic based on the video we saw near the beginning of the talk, and so we see this impact and time-dependent change occurring. We can see the size of the blocks and the volume of blocks that are deposited mid-slope and deposited on the talus cone. In this case, much of the rock has moved into the river as occurred in the real case. So now we can move on to looking at the photographs from before and after this event to really get a sense as to whether our simulation seems realistic or not. This is fairly qualitative, but at the moment it's the progression in the development of these approaches. So we see pre-failure photographs in the middle of this slide of the source zone and deposit zone, and then we see on the right side the blocks that have accumulated in the source zone and on the deposition zone. So this again gives us an ability to start to calibrate the models that we're developing. In the next image, you can see the change detection in the left image. So this is the real data from the comparison between sequential LiDAR data sets. And on the right side, you see the simulated change. So you see again the source zone, the deposition zones. You can see that the particle sizes are relatively large in this simulation on the right side. And as I said, about a year ago, we were limited in the total number of blocks that we could simulate. But as time goes on, we can simulate more and more, and then we can change the resulting size of particles that we're simulating, both in terms of their interaction and their deposition. But the nice thing you see in this image is that we're relatively close in terms of the change in volume. So mid-slope, in real life, 14% was accumulated on the slope. In our simulation, 19%. And on the talus cone, about 20% accumulation. So we're getting at least reasonable simulations with regard to the volumes. Running these simulations in probabilistic senses permits us to think about mitigation of rock falls and rock slides. So in this image, you can see the source zone of another site that we've monitored. We know the change detection from real life, and we've got a simulation here of the size of the fragments and the distribution of the fragments. So when thinking about mitigation, it's essential to understand the volume, the energy, and the position through which rocks fall. So we see the source zone, we see the deposition, and what we have is a map of where the particles end up in these simulations. So in red on this diagram, you can see about 95% of the runout is captured by the ditch, but about 5% of the runout moves across the ditch. And so you can see in this case a simulation that lets us think about future events and how we might mitigate against the rocks that end up going across the track. On the right side, you can see the output from the game engine showing you the position on the slope in terms of volumes. So we see high up on the slope, we see the loss of the material, we see loss of the material partway down the slope, and then we see accumulation of material at the toe of the slope. What's important here is thinking about, from a railway perspective, where the rails are. So we can see on this result at about minus 265 in the unity coordinates on the x-axis, we see where the rail is located, and we can see the material that's accumulated beyond that. But also important from a railway maintenance perspective are the particles that are deposited upslope as well, because as that ditch capacity fills, the next event will move past that location and across the track as material accumulates. So this permits us to think about the balance between maintenance, ability to retain volume upstream of the railway track, and an ability to protect the tracks from these types of events. The next part of the research that we're moving into is thinking about in more detail how rocks fragment. So in this video provided by Mark Fish from Washington Department of Transportation, we see an event where the rock scaler has an airbag, inflatable airbag behind this rockfall, and as the video progresses, you can see the result of that scaling work. So as I play the video, you can see he's continuing to inflate the bag, and now we see the rockfall event occurring. And we can see the fragmentation of the smaller blocks from the larger object, but that the larger object largely retains its original shape, but it has deformed the gravel pad below. So all these interactions of the rock and the material below become important elements for the modeling we're trying to develop. How does gravel retain the energy or dissipate the energy? If it fell on a solid piece of rock, the different outcomes that we can think about. So here are some stills taken from that video. The elapsed time of that event was about 3 seconds. And as you saw in the video, it was a handheld phone video. So the video frame was changing and the scale was changing. But there's enough information here that we can extract information about how that rock fall occurred, the position of the eventual failure, and the amount of fragmentation that's occurred. So this is the kind of information we're now trying to source and develop so that we can really start to calibrate these simulations in a more realistic sense and to start to capture the information about fragmenting rockfalls. So some very simple simulations from game engines in these next couple of videos. In this one, this is an object falling onto the pavement below, and what's built into the cube that you see is some geologically realistic structure. So as I play this, you'll see the block falls and fragments into pieces to show you that this is possible, but again, from a geological perspective, we need to understand where the structures are present and how easily or not they might fracture upon impact. In the next simulation, we see the fate of an object that's being impacted. So to speak about the rockfall itself and then the material it's impacting. So when I run this video, you see a cube and then a donut falling on another object, and you can see the fragmentation, the position of the fragments across the scene. So these are the kinds of calibration runs that we're developing through the game engine so that we start to move towards simulating realistic fragmentation of rockfalls. And the next video shows you a simulation of a real rockfall event from one of our slopes, again with the change detection from LiDAR giving us the volume. And in this case, with the new simulation tools that are being developed in the physics engines, this rockfall is self-fragmenting. So this is not something where we've said we want this to fragment at this time or that time. This is a self-fragmenting rockfall, and you can see how it breaks up as it moves down the slope. So when I play the video, you can see the large block starting at the top of the slope, fragmenting, impacting the slope as it moves down, and then impacting on the talus cone. And you can see that as time goes on, that rock is disaggregating more and more with these different impacts. And one of the challenges of these types of engines is that you can get them to kind of tell you anything you want. You can get them to fragment massively, not fragment at all. And so what we want to do is turn the sort of real in quotes into something where we're confident that we're simulating something close to reality. So in conclusion, I think you've seen hopefully that the remote sensing approaches that we have developed give us really excellent data sets to look at slope stability analysis, especially if we can get multiple vantage points and where we have time sequential models. These types of techniques are more versatile because we can acquire the data very rapidly, and we have increasingly efficient techniques to build the data sets. And we can start to really understand how these slopes are changing. Repeated scans of the rock slopes permit us to look at these small precursor changes. These are not large enough to damage infrastructure, and as I said earlier, they're often not remarked on. But when we have the remote sensing data sets, they give us an idea potentially of the next larger scale failure that might occur. When we can detect these sub-centimeter deformations in advance, that permits us to forecast an impending rock slope failure. And as I mentioned, that depends on the magnitude and rate of the change. And as you saw in the middle part of the lecture, we have a wide range of volumes now, so we can start to really look at the impact of smaller and larger volumes on the infrastructure and on the natural slope. And this gives us calibration data sets for these new generation rockfall models that we're developing. So on the physics engine side, the development is remarkable. It's fast moving, increasing amounts of realistic simulations through these physics engines, because the movies and games that depend on them rely on these real-time interactions as you watch a movie or as you play a game. And so as they're developing these, they're making user-friendly, rapid tools for developing realistic physics. At the moment, as you've seen, we're simulating rockfall events based on real data, but at the moment they're largely looking good in terms of what we can do. What we need to do is move forward on understanding more real events so that we can calibrate the physics engine components to move past looking good and having more confidence that we're simulating something that's close to real. What you can see in the little clip I'm about to show you is something that was released a couple of months ago by Unreal. This is a new game engine that's just been released. And if you're interested, there's a link there for the YouTube video showing the full simulation. It's amazing what they've been doing. But the little clip you'll see just here is of the Tomb Raider, I guess, in this image running through a canyon. A rockfall event occurs, and then they zoom in to show you the shape of the rocks. These represent millions of triangles in the game engine, and they're able to simulate this very rapidly. So it lets us do the kind of work we're thinking about. So I'll just run this, and you can see the heroine looking up at the slope as rock falls occur. They're bouncing down the slope in a realistic sense, depositing, and then you can see a zoom in on the detail that they have on the rock slope. And this is real detail. So they've got the pure geometry of that information. So this gives us an amazing ability to really simulate the world and then the rockfall events that we're working on. So just moving on to the final couple of slides in terms of ongoing research objectives in these railway slopes. And you can see a picture here of one of the locations, again, where the tracks are sandwiched between the river and the slope. And you can see the potential for substantial events occurring. So as we continue to develop these physics engines, and you can see a simulation running now of another rockfall event from several vantage points, we need to have realistic data from rock scaling and from other events to really permit us to calibrate our models in an engineering geology sense, thinking about the geological setting, thinking about the structure present, and thinking about the way the materials behave on the slope. So the next phase is really to try and get a better idea of input parameters, and this requires expert knowledge. So those listening to this talk, if you have interest in any of this, we'd love to hear from you. We're collecting case history data as much as possible. So any data-rich rockfall event tests or inventories that are available. In our work up till now, I didn't have time to show today, we've captured as much publicly available rockfall information as we can find to calibrate our models. As you saw from the video of the rock scaling event and the work we're moving towards now, we're hoping to collect rockfall event data from real scaling or real rockfall events going forward to calibrate our models. And we're really looking for a variety of geological settings in which to do that. So we're starting to capture the influence of weathering and rock type on the fragmentation of the blocks. This requires us to develop and analyze 3D models of the slopes before and after rockfall or scaling activities as much as possible to get these realistic world views and to get the information about the physics of the slopes themselves. And the output of this will be the definition of input parameters and output data related to rockfall simulation that will be useful for assessment and mitigation design. And so the idea eventually is that we will be able to forecast potential rockfall fragmentation always in probabilistic simulations. We'll never get a single answer for these, in my opinion, moving forward to help understand the position of rockfalls, the past height and energy, and then the design of mitigation. So I've provided a few of the publications that reference some of this work. And I want to thank GeoBrugg for the wonderful opportunity to provide this lecture for you. Thank you very much.
Thank you, Dr. Hutchinson. There's a question in my mind that comes up right away. How can your results of rockfall prediction be integrated in the risk assessment procedure? Do you think it will be something like a revolution of the work we do, or do you see it maybe more as an additional information filling the sort of big picture?
Yeah, so I see the simulation of rockfall events as being something that will gradually develop. And as it develops, it gives us more and more information about how to design effective mitigation. So the ability to simulate fragmentation in a realistic sense considering the geological source of the rocks gives us an ability to move from thinking about a single rockfall lump moving down the slope to something that's fragmenting and distributing at the base of the slope, for example. Not all rockfalls do that, of course. Some occur just as is, they don't fragment. So what I think we'll be able to do is a probabilistic analysis to let us look at potential for fragmentation or not, where the rocks will end up or not, and improve our ability to understand the mitigation systems that we're trying to design. So what's the energy? What's the distribution of the rockfalls? It's not something that, as I say, we get a single answer from, but the more we can calibrate these models and the more we can simulate real conditions of fragmentation and impact on the slope, the closer we get, in my mind, to being able to support the design side from a more realistic sense.
And what are the greatest challenges to overcome to make this prediction as reliable as possible?
I think the biggest challenges are twofold. One, enormous amounts of data. So we have huge amounts of data that we're working with, and how do we sensibly extract information from that? How do we think about the way that that can contribute to our design? But I think probably most problematic going forward is making sure that the simulations that we do have some basis in reality. And so anybody can pick up a piece of software, anybody can basically get it to say what they want it to say, or may not understand what it's saying. And so one of the big challenges in simulation is trying to make sure that what you're doing reflects what's happening in the geological reality. And so that's where things like the case histories of the kinds of things you do, where you drop rocks and you look at how they behave and you work on systems to retain them, all of that knowledge comes into thinking about these types of events. So to me, if we want to move towards a much broader acceptance of these kinds of tools and effective use of these kinds of tools, we need to have a simple to use model, we need to have strong calibration cases, and we need to have the ability to ground check our results. Do the results show what we're seeing in reality? Do the results help us in our design? And I think that's the biggest challenge, making sure it's practical, user-friendly, but also somewhat realistic in terms of the results.